left off yesterday. We said that all electrons want a full outer S and P. So in something that has a configuration, a configuration like, in something like, well, this. So just looking at that, who can tell me, and we don't even need to know what the noble gas is, but who can tell me what comes after the noble gas? 3s2. Awesome. So something 3s2. We don't care what the noble gas is right now. You can tell it's 3 because why? It's in the third period. You can tell it's S2 because it's in group 2. So that would like to have a full upper S and P. Well, to fill up the 3s and P would be a lot of work. Much more likely to ditch those 2 s electrons on the third level and drop back. We know that in here we would have 1s2, 2s2, 2p6. Well, that'll do. So we can use that as its full upper S and P. Whatever is going to be the easiest upper S and P to have filled, they'll take. Okay, that's easy. So we're getting to 8. We're counting to 8. We're counting to 8. There are some exceptions to that, though. There are a couple of elements that are satisfied with less than a full S and P. So hydrogen, obviously, because it's only got 1 energy level, is satisfied with 2 electrons. Because hydrogen, if you think about it, is 1s1. If it can fill that 1s, it's satisfied. Boron, and this is weird. You got your periodic table out? Boron, how many electrons is boron starting with? Boron, of all the weird things, because it's starting with 5, usually is satisfied with 6, which is strange, and I am not enough of a chemist, not enough of a particle physicist to explain why, but okay, sure, take your word for it. Here's the part that I find most interesting, and we're going to do these a little later this week, maybe next week. We can have atoms that actually end up with more than 8 electrons. So when we start creating structures for atoms, you're always going to look for 8 connections, 8 connections, 8 connections. Except there will be some cases where we end up with something that looks like it's got 10 electrons around it. That happens, and it'll make more sense when we see examples of it. That happens when we have something that's bonded to stuff that's really electronegative. What does something that's highly electronegative do? Pulls the covers off. So when you've got something bonded to another atom that is very electronegative, it's going to tend to pull those electrons away from the central atom. So that's how we can end up with something that's got what looks like way too many electrons. And when we get to that point, you're actually seeing the d orbitals get involved. Usually we're talking about bonding on the s's and p's in covalent bonding, but when we get into stuff where we have what's called expanded valence bonding, you actually are looking at d orbital involvement. Okay, so we're going to practice doing electron dot notation. How many of you have done electron dot notation? You think you did. Okay, if I do this, does that look familiar to you? Awesome. You probably did this in physical science. And with electron dot notation, we are only showing the valence electrons, and we're showing how many valence electrons there are on any given atom. If you read the, I'm going to say, quote-unquote rules about doing electron dot notation, there are all these patterns. So let's do fluorine. And I'm going to make this my big, if you're using doceri, it's really helpful to have something that's a nice big fat dot. So sodium has 1 valence electrons. valence electrons. I speak English. How many valence electrons does fluorine have? You've got your periodic table out. Stick your finger on fluorine. Discuss with people at your table how many valence electrons do you expect to find there? I hear mutters. Some of them are correct. I think I heard somebody say 4. That is not correct. Okay, 7. I heard a few 7s. Yes. 7 valence electrons. 17 minus 10. And it's only got 1 valence electron to add to be like a noble gas. So we know it's got 7 valence electrons. When we start drawing electron dot notations, if you listen very carefully to the rules, you're imagining that this atomic symbol is surrounded by a bunch of invisible boxes. And each one of those, you'll never draw this again, and each one of those boxes can hold a representation of a valence electron. And you start at the top, and you keep going around until you've gotten the number of valence electrons necessary. Now, here's what I want to tell you. Atoms are not stamped with little letters. You're all aware of this, right? There is no little F on fluorine atoms. There is no little Na on sodium atoms. Doesn't work that way. They're not well labeled. The valence electrons are not really floating in space around the little atomic symbol. These are representations of reality. This is a model that helps us think about the valence electrons. You're laughing now, but I have had people go, but there can't be, they can't move because they're in. No. It's a representation of reality. Okay, that's all it is. It's like a map to help us think about something. The map is not reality. If I draw a street on a map, it doesn't mean the street is there. So when we do electron notation, I'm going to shrink this. Let's practice the electron notation for magnesium. How many valence electrons does magnesium have? 2. So we're going to give it 1, 2 dots. Now, by convention, we don't ever put those on the same side unless we've filled up all the possibilities. So we will put them on opposite sides. If we were being really serious about this, we might think, well, you know, these should go on opposite sides because electrons will repulse one another. Here's what I'm going to tell you. It doesn't matter. Now you can't put them on the same side because we would never see that. But I have had people say to me, but the electron has to be below the letters. No, it doesn't. Again, this is a representation of reality. It is not reality. Atoms are not stamped with their atomic symbol, and the little dots are not in little boxes. It's not the real world. We're using a model to represent things. Because when we get into Lewis structures, people will say, well, I can't move that electron. It has to be on this side. No, it doesn't. Okay, I see a few furrowed brows. So let's do boron. What the heck? How many valence electrons does boron have? Be careful here. It's got 3. Everything in a group is going to have the same electron dot notation. So what about and by the way, Mr. Voorhees is way better at Lewis structures than I am. He sees them intuitively. I never have seen them intuitively, which I actually will argue makes me better at explaining them because I never understood them the first time I learned them. So I had to fight with them. And I've got a really good step-by-step for doing Lewis structures. But, okay. Let's do, our old friend carbon. How many valence electrons? You got something that looks like that? Yeah. This is easy. You're just looking at the number of valence electrons, you're sticking the dots around them. What if we do oxygen? And yeah, if we do the Voorhees method, I like that. Made up with something like that. My dots aren't level, it's fine. Once again, these are not reality, these are a representation thereof. Okay, fairly simple. Good. Okay, so here I am showing you two fluorine atoms. Whoops. Two fluorine atoms. Here's the neat thing about Lewis dots. We can show covalent bonding with Lewis dots. What is covalent bonding by definition? What are they doing? Sharing electrons. They're sharing a pair of electrons. They feel like they've got a full pair. Well, we know that fluorine in the wild exists as a diatomic molecule, F2. So these two fluorine atoms will bond somehow to form a diatomic molecule. And this is where I've had students say, but the F's are on the the dots are on the wrong side. They're not really there. So we can just as easily take this, stick it over here. And if we put these together, hey, guess what? Everybody feels like they are surrounded by 8 electrons because this fluorine feels like it's got 2, 4, 6, 8. And this fluorine feels like it's got 2, 4, 6, 8. Never mind that they're sharing that center pair. They both feel like they're surrounded by 8. And that's what we're going to do when we do these bonding structures. We're going to see them share electrons again and again and again. Carbon is fantastic. So I'm going to draw my carbon again. Carbon does a really great job bonding to other carbons and bonding to hydrogens and bonding to lots of things. Carbon forms 4 bonds. It's got those 4 valence electrons, so it forms 4 bonds. So if you can count to 4, you can do organic chemistry. If you can count to 4, you can do organic chemistry. So I'm going to put this carbon over here, bonded to this carbon. And very often in nature what we find is carbon bonded to hydrogen. Hey, look at that. Let me shrink everything else. And move this down a little bit. So often, yeah, we find carbon sharing electrons with a lot of things. These are covalent bonds. This is one way we show covalent bonds using electron dots. And that's not a very neat carbon. When we get to Lewis structures, we'll talk more about ways that we neaten these drawings up. Now sometimes it happens, and I'm going to copy this. Copy. We have what are called multiple covalent bonds. And that's when we have 2 atoms that are sharing more than 1 pair of electrons. So I sort of talked about this a little bit yesterday with my friend Mike. Actually, he's really my husband's friend. I don't really claim him. And the potato cannon that he decided to run on MAP gas, which has a double bond, a double or triple bond in there, which is shorter, higher energy. That is a multiple covalent bond. It happens a lot. It happens in carbon a lot. Double covalent bonds, sharing 2 sets of atoms. Triple covalent bonds, sharing 3 sets of atoms. I don't know of anything on the planet that does a quad bond. There may be something, but I don't know of anything. Double and triple bonds, though, are really, really common. So let's take a look at what might happen if, in fact, we didn't have these hydrogens here. I'm going to zoom in on this. And if anybody here is lucky enough to get to take organic chemistry, you will do more of this than you ever dreamed possible. So right now we've got these carbons, and this one feels like it's surrounded by 2, 4, 6. The hydrogens are happy with 2, 2. This carbon feels like it is surrounded by 2, 4, 6. But there are those 2 electrons up here unshared. And there's nothing worse than a single unshared electron like that. It's always going to pick something else up. Always. So what often happens is the carbon ends up sharing 2 pairs of electrons. That is a carbon double bond. So, how many electrons does each carbon feel like it's surrounded by? 2, 4, 6, 8. 2, 4, 6, 8. The carbon counts to 8, it's happy. That's a double bond. We can triple bond stuff too. Nitrogen is famous for triple bonding. So nitrogen starts out looking like this. How many covalent bonds can nitrogen form based on that picture? Hold up fingers. 3. Nitrogen can form 3 bonds. So we end up with a lot of compounds. Well, we end up with things like ammonia. This is household ammonia, right there. The hydrogens count to 2, the nitrogen counts to 8, everybody's happy. But we also end up with nitrogen sharing all of those bonds, especially with carbon. Oh, wait. Yeah. And of course then the carbon has to be bonded to something else. Like that. That's cyanide right there. That's a triple bond. The carbon and the nitrogen are sharing 3 pairs of electrons. As I said yesterday, multiple bonds tend to be shorter and tighter. You had your rubber bands. Hopefully those all ended up in safe places. And nobody got in trouble for having a rubber band later in the day. Just don't tell them where you got it. They tend to be shorter, they tend to be stronger, they tend to have higher energy. So like I said, don't run your propane-powered potato cannon on MAP gas if you did all the calculations for the amount of energy contained in propane. I'm sorry. Did nobody say, like, hey Moser, you're out of order, you missed one? No? Huh? Is the right order? Okay, I thought this one should come before multiple bonds. Oh, yeah. I screwed up. I think people got to tell me when I screw up. I need all the help I can get. Seriously. Okay, so what we're going to start doing is going from, yeah, it's frozen, but that's okay. We're going to start going from those electron dots to what are called Lewis structures. And Lewis structures are what we just did. It's where we take the electron dot symbol for an atom, and we start forming bonds, and we start drawing the entire compound with dots representing valence electrons. Okay, we're going to cut the recording off here and then start the Lewis structures.